Hi there, Arthur here. In this short video, I would like to show you ZAMA. ZAMA is a blockchain protocol that allows you to use a fully homomorphic encryption. If you never heard of it before, I think it's worth to check it out. Some people are referring to it as a holy grail of cryptography because fully homomorphic encryption allow you to encrypt the data and then perform some operations directly on the encrypted data. And usually, if you want to do some computations, you need to decrypt the data beforehand. But if you can do it on encrypted data, then it makes it a very interesting concept that can be used in blockchain and Web3 space in general. So in this video, I would like to show you a simple application that I did. Is a rock, paper, scissors game, but implemented with ZAMA, the fully homomorphic encryption framework protocol. So if you would like to check out this application, it's linked down below. So you can check the code on the GitHub and just play it with it locally on your machine. But now I will go through this application, what I did, how this works, and actually what problems it solves. So if you would like to play a rock, paper, scissors game in regular blockchain like mainnet, Ethereum, Polygon, or whatever, the main problem with playing such games is that every transaction that goes to the smart contract is public and all other people or other players can check what was my choice in this game. So if I do the scissors and I know that my opponent will do scissors as well, then of course the game is pointless. So it's very important to keep our choices secret and just reveal them once we both submit our choices so we can set who is the winner. And on public blockchains it's tricky because obviously we always can check the transaction of the first player and then based on that make our decision. However, here, thanks to ZAMA and fully homomorphic encryption, we can do a very interesting thing. So we can have a regular Solidity smart contracts but with some extra operation. And for instance, here, if I submit my encrypted choice, then I can authorize smart contract or some other public wallets to actually decrypt this information or do some operations on this data while it's encrypted. So it's very interesting because both players can submit their encrypted choices, and then we can have the function like here, compute the winner FHA, which does some computations over the encrypted data, which allows us to reveal who was the winner of the game. And then the end result of the game again could be publicly decrypted, or just we can set that certain wallets or certain smart contracts are able to decrypt this data. And the SDK, the interface for that is quite straightforward. Here, for example, I have WAGMI hook. So inside of it, whenever I'm sending the transaction to the smart contract, I'm able to encrypt and specify that the certain contract address should have access to this data. So I'm pretty sure that you are curious how this application works. So I will first start the local hard hat chain. Then I will deploy the contracts. I will generate types for it and then make sure that the front-end application is up and running. And now we can see initial state of the game. So I will click start new game. Of course, I need to send a transaction to this smart contract. And then I can choose my move. So I will go with scissors. And of course, I have to send a transaction. Now I will switch to second account. I will join game. And then I will take paper. So the second player should be loser. And now let's decrypt the results. We have to send a transaction. And we can see that player one wins. And of course, all of that is implemented here. This whole smart contract is a bit different than regular Solidity smart contract because here we have some FHE operations. If you are curious how this works, just check the repository. And I also prepared tests for this particular contract. So we have all the examples covered here. So all kind of scenarios, who can decrypt the results. We have also checked that if the game is started, other players are not able to join it, that the same players shouldn't be able to join it twice, and so on. So we have here all the scenarios, and here also you can learn how actually interaction with these smart contracts is a bit different. So for example, before sending the transaction that I would like to pick the paper, you can see that we have here some operations where locally on our device we are generating an encrypted input, and then we are submitting the encrypted input along with zero knowledge proof that indicates that from our wallet the encryption was done. We're pushing it to the smart contract, where afterwards the results can be fetched. And of course, I'm not yet familiar with all the details of how ZAMA works, but from what I got from the paper, the whole protocol has some relayers and some on-chain and off-chain components that are allowing this whole encryption to work. So it's not only that we have smart contracts deployed to Sepolia or Ethereum mainnet, but also on these networks we need to have reliers, we need to have pre-deployed smart contracts that are used behind the scenes by FHA library, which, by the way, it's quite easy to use. You just have to import it into your Hard Hat or Foundry project, and then you can start playing with this application. So that's all. Let me know what you think about this cryptography in the comments. Thanks for watching, and see you in the next one.